faithfully delivering value, exploring great books from around the world. Hello, this is Sally's Book Talk. Today, the book we're diving into for you is Death by Reason, Lavoisier and the French Revolution. The author is Madison Bell, a renowned American writer who excels in historical themes and biographical works, and has been nominated multiple times for the National Book Award. What do you know about Lavoisier, the father of modern chemistry? And how do you view his ultimate fate? Welcome to share your thoughts in the comment section. Lavoisier was a French scientist hailed as the father of modern chemistry. He discovered oxidation, confirming oxygen's existence, named elements like oxygen, nitrogen, and hydrogen, created the first element table, formulated the law of mass conservation, and debunked medieval alchemy. With these achievements, he laid the groundwork for chemistry to evolve from mysticism into a modern science, and played a key role in giving France an edge over Britain in 19th century scientific rivalries. Yet, this brilliant scientific star was executed at the height of the French Revolution. Ironically, the revolutionaries championed science and reason to replace feudal superstitions. They even invented a goddess of reason for worship. Yet this revolution, touting rationality, sent the world's most rational mind to the guillotine. This perfectly mirrors the book's title, Death by Reason. How did this tragedy unfold? What kind of person was Lavoisier? What complex relationship did he have with the French Revolution? Next, I'll cover him as the precocious youth devoted to science, the genius who revolutionized chemistry, and the public official who faced resentment. 3 parts tell the story of this scientist's legendary life and tragic end. Okay, now for part 1, the precocious youth devoted to research. Lavoisier's full name is Antoine-Laurent de Lavoisier, born into a family of lawyers. His great-grandfather worked as a bailiff in a small town near Paris, living comfortably. His grandfather became a lawyer and married a wealthy woman, while Lavoisier's father, Jean-Antoine, climbed even higher. In his youth, he studied law in Paris, and after graduation, joined the Paris High Court as a lawyer. In 18th century France, judges and lawyers held high status, entitled to wear robes signifying noble-like rank, known as the robe nobility. Of course, the Lavoisier family didn't have noble titles, but they rose into the upper class, living affluent and respected lives. On August 26, 1743, Lavoisier was born in Paris. At age 6, his mother passed away, and he was cared for by his aunt. From a young age, Lavoisier was quiet. While other kids were playing, he was alone, reading and thinking. Everyone thought he was a precocious boy. At age 11, his father sent him to the Mazarin College, and a few years later, to the Paris Faculty of Law to study law. His father's intention was clear. He wanted Lavoisier to follow in his footsteps and become a lawyer, and Lavoisier lived up to expectations. At age 22, he earned his law degree and joined the Paris High Court as a lawyer. But ultimately, Lavoisier didn't become a lawyer, because his heart already belonged to scientific research. During his studies, Lavoisier was exposed to mathematics, physics, chemistry, geology, and botany, and he became deeply fascinated, igniting his ambition to devote himself to scientific research. Here, some background is needed. Modern science was just emerging, and the development of various disciplines was highly uneven. Physics, thanks to Newton's discovery of universal gravitation and formulation of the 3 laws, had already established a relatively complete body of knowledge. Mathematics, with the joint invention of calculus by Newton and Leibniz, along with the long-standing algebra and geometry, also achieved leapfrog development. In contrast, chemistry, which Lavoisier was most interested in, was in its infancy and appeared very rudimentary. Modern chemistry was born from alchemy. What is alchemy? Simply put, it's about transforming base metals into precious metals. Medieval alchemists proposed various theories and conducted numerous experiments trying to turn lead, copper, iron, etc., into gold and silver, or even the elixir of immortality. During the process, alchemists did discover and study some chemical phenomena thus accumulating certain chemical knowledge. But they treated this knowledge as exclusive secrets, and to prevent leaks, deliberately expressed it in obscure, difficult to understand language that outsiders couldn't comprehend. For example, one alchemist left a record like this: "The king dismissed all servants during his bath, leaving only one guard to heat the bathwater." Historians struggled to decipher the meaning of this sentence. Melting lead into liquid and adding several metals to it could produce gold. Such obscure jargon, even if spread, how many could understand it? It was a secret known only to a few alchemists. Moreover, these secrets had no scientific basis and couldn't be considered true chemistry. This seriously hindered the development of chemistry and kept a large number of talents out. And mark by read. From the 14th to 16th century, the Renaissance swept through Europe, gradually dispelling the ignorance and superstition that had shrouded the Middle Ages with science and reason. And British thinker Francis Bacon proposed that observation, experimentation, and induction form the foundation of scientific research.
Influenced by this, British scientist Robert Boyle pointed out in The Skeptical Chymist that when experiments don't match theories, either redo the experiments or revise the theories. Never ignore it like alchemists did. Boyle also opposed alchemy's obscure jargon.
He advocated that scientific language should be clear and precise, not deliberately mystifying. German chemists Becker and Stahl proposed the phlogiston theory, historically the first rational and clear explanation of combustion, advancing chemistry. Through these individuals' relentless efforts, chemistry gradually broke free from alchemy to become an independent discipline. And by the mid-18th century, many European institutions offered chemistry courses, like the 3-year program at Mazarin College, where Lavoisier studied. Lavoisier attended classes eagerly. Due to his strong interest, he later studied under renowned French chemist Rouelle for a year of systematic learning. Yet after 4 years, the results were unsatisfactory. After all, chemistry had just separated from alchemy and remained immature. Many chemists still fantasized about alchemy, hoping to turn base metals into gold through experiments, which dissatisfied Lavoisier. Chemical theories were either disconnected or contradictory, experimental methods crude, and filled with unverified assumptions.
They even lacked basic scientific logic.
In short, to Lavoisier, chemistry had no essential difference from alchemy. Compared to mathematics and physics, chemistry was far less scientific, so he resolved to study chemistry from scratch. Initially, Lavoisier's father disagreed because scientific research not only provided no income but required scientists to fund themselves. But Lavoisier assured his father he'd conduct research during spare time, without affecting earnings, finally gaining paternal understanding. In 1764, the same year he joined the Paris High Court as a lawyer. Filled with scientific passion, Lavoisier participated in the Paris street lighting design competition, initiated by the French Academy of Sciences, winning a gold medal. In May 1768, he was elected to the French Academy of Sciences, based on 2 papers, officially becoming a scientific researcher. From then until the outbreak of the French Revolution over 20 years later, Lavoisier diligently researched, making outstanding contributions to establishing and perfecting modern chemistry. This leads us to part 2, the scientific genius who revolutionized chemistry. Lavoisier had 4 major contributions to modern chemistry. First, discovering and naming oxygen to overthrow the phlogiston theory, which explained combustion phenomena. It was proposed in 1703 by German chemist Georg Stahl. Stahl believed all combustibles contained tiny active particles called phlogiston. Combustion occurred when phlogiston escaped or transferred between objects. For example, burning sulfur released phlogiston, turning it to sulfuric acid. Boiling the acid with turpentine would transfer phlogiston back, reverting it to sulfur. Similarly, calcinating metal released phlogiston, leaving residue. Heating it with charcoal transferred phlogiston back to the metal. Sounds plausible, but who's actually seen phlogiston? Chemists conducted many experiments, with results mostly supporting phlogiston theory. By mid-18th century, phlogiston theory became chemistry's cornerstone. Lavoisier disagreed. He noticed phosphoric acid gained mass after phosphorus burned, same with sulfuric acid from sulfur. Wait, if combustion releases phlogiston, objects should lose mass. Why gain weight? Lavoisier boldly speculated combustion involved chemical reactions with an airborne element, adding mass. In other words, air was a compound of multiple elements. 18th century chemists universally considered air an indivisible fundamental element. Lavoisier's view was undoubtedly heretical, but Lavoisier resolved to prove himself. In March 1775, he conducted his famous 12-day experiment. He poured mercury into a retort, connected via mercury trough to a glass bell jar filled with air. Heating the mercury made it glow, forming red residue. By day 12, residue stopped increasing, unchanged with further heating. Lavoisier ended the experiment, calculating air volume in the bell jar decreased by 1/5. Clearly, it was this vanished gas combining with mercury that formed the red residue. To further confirm, Lavoisier heated the red residue at high temperature and collected the released gas, which turned out to be exactly 1/5 of the original air volume. Lavoisier named this gas oxygen, derived from Greek meaning acid-forming. Lavoisier believed all acids contained oxygen. Of course, this idea was later proven wrong, but the name oxygen stuck and remains in use today. Besides oxygen, about 4/5 of gas remained that couldn't support combustion, named nitrogen. Lavoisier also noted small amounts of fixed air in the atmosphere, what we now call carbon dioxide. Chemists hadn't yet understood its nature then, naming it fixed air for its inertness, consistent with modern science. Lavoisier concluded combustion wasn't phlogiston release, but a violent reaction between substances and oxygen releasing light and heat. Thus, the phlogiston theory collapsed. Actually, Swedish chemist Scheele isolated oxygen before Lavoisier, but conceded discovery rights due to belief in the four-element theory. This brings us to Lavoisier's second major contribution, the complete refutation of the four-element theory. As mentioned, chemists then considered air an indivisible fundamental element. This theory originated from Aristotle's four elements: earth, air, water, and fire combining to form all matter. For millennia, this was accepted as truth. Astronomy, physics, medicine, chemistry, all built theories upon it. But Lavoisier's experiment showed air wasn't elemental, as it decomposed into oxygen, nitrogen, CO2. This breakthrough raised the question, can earth, fire, and water be decomposed too? In June 1783, Lavoisier collaborated with French mathematician Laplace on water synthesis. They injected oxygen and hydrogen, discovered by British chemist Cavendish, into a mercury-filled bell jar, ignited it, and produced water. Later, Lavoisier designed another experiment, successfully decomposing water into oxygen and hydrogen. In his report to the French Academy of Sciences, Lavoisier declared water wasn't an element, but composed of oxygen and hydrogen. As for Earth, it could be broken down into water and minerals, so it couldn't be fundamental. Now, only fire remained. Lavoisier understood fire as the light and heat produced during combustion, a description of the phenomenon that failed to reveal its essence. The book's author believes this wasn't due to Lavoisier lacking intelligence, but limitations of his era. Modern research shows fire consists of plasma, a state of matter beyond gas, solid, and liquid. Clearly, Lavoisier in mid-18th century couldn't have accessed such research conditions, missing this discovery. Regardless, expelling earth, air, and water from fundamental elements was enough to overturn the four-element theory. Combined with overthrowing phlogiston theory, Lavoisier dismantled chemistry's foundation, causing major scientific upheaval. While supporters were many, opposition was significant, including the British chemist who first isolated hydrogen. Cavendish firmly believed hydrogen was phlogiston, that his experiments reinforced phlogiston theory. Similarly, French and German chemists rejected Lavoisier's conclusions. Modern observers might see them as rigid and obstructing progress, but this is a misunderstanding. Their skepticism came from scientific grounds, was normal discourse, and their concerns were valid. First, limited by conditions, Lavoisier's experiments were imperfect, with debatable precise conclusions. More crucially, if you dismantle chemistry's foundation, how can research continue? Lavoisier recognized this. Destruction must precede creation, and destruction was complete. Next came establishing new theories. Thus came Lavoisier's third major scientific contribution, reforming chemical nomenclature, creating the element table, and building modern chemistry's framework. As mentioned, modern chemistry emerged from alchemy, which used obscure jargon for substances. For example, take the king's crown and boil it meant nitration. Put a rod of long fingers in the retort referred to sal ammoniac, ammonium chloride. Since the 16th century, chemists struggled to purge alchemy's influence with little success. Not just beginners, even experienced chemists were often baffled, turning scientific research into deciphering cryptic texts. Lavoisier resolved to end this chaotic situation. In 1787, he collaborated with 3 colleagues from the French Academy of Sciences to publish Chemical Nomenclature. Lavoisier proposed naming substances based on chemical analysis results, such as oxygen, nitrogen, and hydrogen. Indecomposable substances are called elements. Pure substances made of identical elements, like oxygen 2 oxygen atoms and ozone 3 oxygen atoms, are simple substances. Materials composed of multiple elements, like carbon dioxide and sodium nitrate, are compounds. For practical use, Lavoisier compiled a table of confirmed chemical elements, including oxygen, nitrogen, hydrogen, plus sulfur, phosphorus, iron, totaling 55. Over 80 years later, Russian chemist Mendeleev built on Lavoisier's foundation, creating the periodic table and modern chemical systems that severed chemistry's ties with alchemy. Since then, chemists have used precise, concise language to express theories and describe phenomena. Interestingly, because Lavoisier wrote in French, the language temporarily became the universal scientific tongue. It can be said Lavoisier also boosted French's international standing. Finally, Lavoisier's fourth major contribution, proposing the law of conservation of mass and introducing mathematical tools to chemistry. Working long hours in the lab, Lavoisier noticed boiling water left solid residue in containers. Where did it come from? Once, he boiled 3 pounds of water in a distillation flask for over 100 days. Residue indeed formed at the bottom. Weighing it showed approximately 1 gram of residue, exactly matching the flask's mass loss, proving it dissolved matter from the heated glass. He deduced that chemical reactions merely transform matter between states without changing total mass, where elements neither increase nor decrease. Lavoisier termed this the law of conservation of matter, today known as the law of conservation of mass. Additionally, algebra became essential for calculating masses and analyzing results. Thus, Lavoisier introduced mathematical tools into chemical research. He also emphasized that chemistry should increasingly use mathematical language for greater precision and scientific rigor. And this laid the foundation for the emergence of chemical formulas. That concludes Lavoisier's major contributions, each groundbreaking in its own right. Thus, even during his time, Lavoisier was highly acclaimed as the scientific genius who revolutionized chemistry. Given time, he would undoubtedly have made more discoveries and greater contributions. Lavoisier himself was full of confidence, unaware that drastic external changes would soon engulf him. Ultimately, this once-in-a-century genius died on the guillotine in his early 50s. What could Lavoisier have possibly done to deserve this? In Part 3, The Resented Public Official, I'll reveal the answer. So far, we've only presented Lavoisier the chemist, but he had other social roles. The most significant was his role as a public official. In 1768, the year he joined the French Academy of Sciences, that same year, Lavoisier also decided to join the general tax form as a tax collector. France then operated under the tax farming system, where the king outsourced tax collection to private individuals. Tax collectors kept surplus after remitting a fixed amount to the crown. Now, thus, it was a lucrative position with fierce competition. Lavoisier paid a fortune for this role. Was he really that greedy? Not at all. His purpose was to fund scientific research. Some context. The 18th century had no professional scientists or dedicated research institutions. Take the French Academy of Sciences, which Lavoisier joined. It was merely a platform for scholarly exchange, without further functions. Scientists had to self-fund experiments while supporting their families. Thus, all scientists needed jobs, Lavoisier included, and tax collecting was undoubtedly an excellent choice. Records show during his 20 years as tax collector, Lavoisier earned 200,000 livres, equivalent to $50 million today, making him wealthy. This proves research requires funding. Thanks to his substantial income, Lavoisier acquired precision instruments. Just one gasometer for his water synthesis experiment with Laplace cost $250,000. Today, that would be $250,000, with the full setup costing millions, unaffordable for ordinary people. So it's fair to say, without his tax collector earnings, Lavoisier's research would have been unsustainable, let alone revolutionizing chemistry. The problem was tax collectors attracted hatred, foreshadowing Lavoisier's tragic end. Why were tax collectors hated? Simply put, to maximize profits, tax collectors often overtaxed, some even extorted, naturally angering taxpayers. France's largest taxpayer group was the emerging bourgeoisie, who resented tax collectors most deeply. They constantly criticized in their controlled media, with Lavoisier as a prime target. To be fair, Lavoisier wasn't greedy and lived modestly, but his fame made him vulnerable. Tall trees catch the wind, as they say. Worse, Lavoisier applied scientific rigor to tax collecting. He examined every aspect of tax farming, plugged loopholes, used mathematical tools to collect every penny owed. His reforms increased revenue and efficiency, faithfully delivering value, exploring great books from around the world.
Hello, this is Sally's Book Talk.
Today, the book we're exploring for you is Death by Reason, Lavoisier and the French Revolution. The author is Madison Bell, renowned American writer specializing in historical themes and biographies, multiple National Book Award nominee. What do you know about Lavoisier, the father of modern chemistry? How do you view his ultimate fate? Welcome to share your thoughts in the comments. Lavoisier was a French scientist hailed as the father of modern chemistry.
He discovered oxidation, confirmed oxygen's existence, named elements like oxygen, nitrogen, hydrogen, created the first element table, formulated mass conservation law, and debunked medieval alchemy.
These contributions laid chemistry's modern foundation, freeing it from mysticism, and gave France scientific advantage over Britain in the 19th century. Yet this brilliant scientific star was executed at the French Revolution's height. Ironically, revolutionaries championed science and reason to replace feudal superstitions. They even created a goddess of reason for worship, yet this rational revolution sent the world's most rational mind to the guillotine. This perfectly mirrors the book's title, Death by Reason. How did this tragedy unfold? What kind of person was Lavoisier? What complex relationship did he have with the French Revolution? Next, I'll cover him as the precocious youth devoted to science, the genius who revolutionized chemistry, and the public official who faced resentment. 3 parts tell the story of this scientist's legendary life and tragic end. Okay, now for part 1, the precocious youth devoted to research. Lavoisier's full name is Antoine-Laurent de Lavoisier, born into a family of lawyers. His great-grandfather worked as a bailiff in a small town near Paris, living comfortably. His grandfather became a lawyer and married a wealthy woman, while Lavoisier's father, Jean-Antoine, climbed even higher. In his youth, he studied law in Paris and after graduation joined the Paris High Court as a lawyer. In 18th century France, judges and lawyers held high status, entitled to wear robes signifying noble-like rank, known as the robe nobility. Of course, the Lavoisier family didn't have noble titles, but they rose into the upper class, living affluent and respected lives. On August 26, 1743, Lavoisier was born in Paris. At age 6, his mother passed away, and he was cared for by his aunt. From a young age, Lavoisier was quiet. While other kids were playing, he was alone, reading and thinking. Everyone thought he was a precocious boy. At age 11, his father sent him to the Mazarin College, and a few years later to the Paris Faculty of Law to study law. His father's intention was clear. He wanted Lavoisier to follow in his footsteps and become a lawyer. And Lavoisier lived up to expectations. At age 22, he earned his law degree and joined the Paris High Court as a lawyer. But ultimately, Lavoisier didn't become a lawyer because his heart already belonged to scientific research. During his studies, Lavoisier was exposed to mathematics, physics, chemistry, geology, and botany, and he became deeply fascinated, igniting his ambition to devote himself to scientific research.